honored to have Professor Yan here. He's going to be having a new post in the coming February. OK， 很高兴的今天能请到这个严教授，严嘉义教授，这个台大机械系的严教授，来为各位同学分享他关于这个应用在这个生意上这个机器人的这个微创机器人的一些手术应用。好 ，Without further ado, let's welcome Professor Yan to the chat. Thank you.
It is actually my great honor to be able to come here and share some of our results with you. And I was told that many of you are not comfortable with hearing lecture, so I will conduct my lecture in English. So, tell you the truth, I'm not so sure about my English. So, if you have any questions, you can always raise your hand. I'll try to stop myself and try to provide a better explanation. And if that doesn't work, I will switch to English. Okay, so what I'm going to talk about is some of our recent research on using robotic arm for minimum invasive surgery. And you can see that I have listed a lot of our colleagues and my students. Professor Min-Chi Ho is the head of the Department of Surgery at National Taiwan University, but the Zhubei department. And Professor Yao Chen is from WE of National Taiwan University, and these are some of my students. This is what happens when you go, if you get a chance to go into a minimally invasive, actually a surgical environment. You get these lightings, and suppose you are undergoing a minimally invasive surgery. What they do is they pump up air into your belly so that there will be room for operation. And then you see that there are a lot of people there. If I recognize correctly, because of the mask, this is Professor Ho, who is the main surgeon who is operating on the patient. And then you can see that there are a lot of people around. They were there to help because when we started the minimally invasive surgery, what they do is they will touch at least 3 or 4 holes on your belly. One of it is for pumping air into your belly so that it remains kind of swell and you will have enough room for operation. And then there will be 2 holes for the operating tools, one for either the scissor or for the cutting tool, and then the other one for either nipples or some kind of grabbing tool. And then there will be another entrance hole for the stick. The surgeon needed to see, so there will be another hole for the surgeon to look at for a endoscope to go in to take the picture out. So basically, when the surgeon is performing his operation, the surgeon look at the screen and perform the operation with these tools. So basically these operations are now very, MIS is now a very kind of matured and a very popular operation, and there are a lot of systems available already. And Da Vinci is one of the very famous tool or system. But if you look at the system, it is a very bulky and very large system, and you needed a lot of setup, and also it is a very expensive performance. And if the patient has to go through these performances, they can be very expensive. So what you saw before with Professor Ho's operation would require less preparation and would be a lot easier to perform. So what we're trying to see is, first of all, we don't want to compete with Da Vinci. So we're trying to see if we can just do part of its performance and probably do even a better job. And of course, what we're trying to achieve is more than just achieving the operation requirements. We also try to see if we can have our robot walk around human. For example, you have a surgeon there, and the robot will work with the surgeon. And that is not really a new idea. So if you look at some of the literatures, this is a system done by UCLA. You guys probably have heard of it. It is an eye surgery tool, and what they did is you see this is a very strange setup. What it's for is when we operate on the minimally invasive surgery, we use only a very small entrance hole, and we will try when we operate, we will always observe this entrance wound so that you don't tear the wound, and all the procedures will have to go through this hole. So this is what they do. They use this very strange mechanism to make sure the tool operates around the hole. And what we call this hole, we call it remote center of motion. So when the robot operates, you always observe this. We call it RCM, and so that when the robot operates, it doesn't tear the wall. Now for the endoscope, we do have to think about quite a few things. The surgeon will want to look at certain image or certain point of view of the patient, and so usually the surgeon will either adjust the endoscope, and if you recall what I showed you before the real operation, there will be one surgeon assistant. I'm not sure how they call it in English. The assistant will hold the endoscope, and the surgeon will tell him move it upward, downward a little bit, to the right, to the left. And suppose if you recall the image, you will see that everybody is cramped together, and so this assistant will have to kind of sneak his arm under the pit of the surgeon and try to hold the endoscope in place. So what we're trying to do is, first of all, we want to see if we can achieve an endoscope holder that will basically hold the endoscope, but also when the surgeon moves, it will somehow try to avoid getting in the way. And this is one system. If you guys are familiar with your own professor's work, Professor Song Kai-tai worked on this system. And what they did is this is a system developed by Pyrene technology. And it is, if you look at it, it is a very neat and a special purpose system. What it does is it holds the endoscope here. And if you look at it, it's got this very neat mechanism. When it moves, you always move around the remote center of motion, so that it will automatically observe RCM constraint and then moves it and operates the endoscope. And they use two input devices. One is you see this foot pad, and the surgeon will step on the foot pad and try to move the foot pad and use the foot pad to control the motion movement of the robot. And they also have a microphone that the surgeon can wear on his head, and that didn't work very well because I saw it operate, and the surgeon tried a lot of commands like up and down, and somehow I can see he was always trying to repeat up and up, and the thing doesn't really respond. So that's one thing, and this is how the remote center of motion works. And of course, there are also researches on how the doctor view these endoscope holders. And I'm not going to go through all the details, but the doctor didn't really like all these ideas because when you have to step on the pedal, your foot gets very tired. And if you always have to look at the screen, you have neck injury and stuff. So we're trying to see if we can come up with a more friendly environment. Now, the first part of the task is to model the endoscope. And if you look at endoscope, there are usually the endoscope has this flexible lens in front of it. So we need to somehow come up with a model for the lens. And this I will go through a little bit more detail later. And also, we also worry about the singularity of the robot. So we also try to do this singularity avoidance. Now, to go into the patient, usually you can see, sorry about the Mandarin, but this is, there are three wounds, three entrance wounds. And one is probably for the tool, the other one is for endoscope, and the doctor has two hands, so he usually holds two tools on the both hands. So you can see that the laparoscope usually comes in from somewhere near the, what do you call that, the belly button, and look into the womb. And this is usually for liver operation. Now this is how the thing goes, and we wanted to make sure that the robot performs as it should. So this is, if you are working on robotics, you see a very standard robotics equation. So we're not going to go through the detail, and we break up the task into first establish the posture control to come up with the right attitude, and then we input a command to make sure the robot follows the trajectory. But here we are still at this holding position part. Now, what we're trying to do is, in addition to holding the endoscope at a fixed position, we wanted to make sure that first there's a task control, so that when the robot moves, you will observe the remote center of control, remote center of motion. And then we needed to have a way to get the robot to cooperate with the surgeon. So when the surgeon somehow push the robot a little bit or give the robot a nudge, the robot will try to avoid the surgeon. So we needed this impedance control so that when the surgeon do that. But if we wanted to achieve these tasks, they kind of contradict each other. One is to hold the remote center of motion. The other is to move away. So what we needed to do is we needed a way to have the robot move away according to the surgeon's nudge while maintaining the remote center of motion. And that we first use the no space position. And this is actually pretty intuitive. For example, if suppose this is the robot and we are holding it there. Now if the surgeon started to nudge it, to push it, then what the robot arm should do is just avoid it. Right? So a very intuitive idea is when we move, we try to move in a way that does not change this point. So what we do is we project all the motion into a new space of this point. And if you know what I mean, but later I will show you how it is. So basically, when we have external force, we try to project it into the new space so that these forces only act upon the dimension that does not affect the remote center of motion. Of course, you guys might might be worried a little bit. Let me show you how it comes out. So, in addition to what I showed you before on maintaining the position, we have an extra loop on no space filter, so that when external force comes in, you will end up with a change of the trajectory, but the trajectory will change in a manner that does not affect the remote center of motion. And we actually tried it in the simulation, and you can see that when we'll try to hold this robot is a 6 degree of freedom robot, so there are different ways we can play with it. And this is the situation where we try to hold the attitude of the end effector, and while we move the arm around. And also we can hold a point. When we apply the forces, we try to filter it so that it only feels a torque around the remote center of motion, and so that when every motion it does is moving around it because you only feel the torque. Okay, so this is supposed to work. This is a preliminary result when we apply. This is a very expensive 6 degree of freedom torque sensor. That's what you see. Okay. Now, we also try to see. You can see that demonstration. The surgeon has to touch the robot to make the robot fairly smooth. So we also try the vision based. We use a Kinect to kind of look at the robot and then also look at the surgeon. Of course, I didn't have the doctor play with me, but I have my students there. Now, these are some of the avoidance analysis, meaning when we get certain push, how do we respond to the push? So that's not important. This is and this is supposedly the remote central motion. And so this is my student is simulating the physician. So when he comes close to the robot, you will try to avoid the physician and try to still maintain the remote central motion. Okay. Now another problem comes up. When you see the student comes close to the robot, you want to calculate where is the shortest distance between the surgeon and the robot. So this is what we did next. We try to, this is a simulated robot, and our student comes around and we use Kinect to capture the posture of the person, and then we have the simulated robot, or simulated the robot within the virtual robot, and we can calculate the distance. And that distance is kind of complicated because if you are only trying to calculate the distance between two unparalleled lines, very standard. But then we have actually some the line is not infinite, so you have end point of the arms, and it becomes a little bit more complicated. And so this is how in the real situation, when the robot moves, my students can also move it. We can always try to come up with the shortest distance between the robot and the surgeon. This went on for a bit, and then we realized it really doesn't help because if you recall the picture when I first showed you, you'll notice everybody's cramped together. Although if you are familiar with Kinect, you know it can capture like at least 6 persons simultaneously. But if everybody is cramped together, you will have problems with it. So we actually gave this up and go back to the touching performance. Okay, now if you recall, when I first showed the endoscope, there's a snake. We call it snake lens, but I think the official name for it is flexible endoscope or flexible lens. And if you have this flexible lens, you can see this is the assistant. His hand is beneath the surgeon's arm, and they were just trying to. The surgeon was trying to operate on. I believe he was trying to remove the guts. And, you can see that everybody's cramped together. So you have this. Sorry about the twist, but the distortion. But basically, the idea is when the robot has to move away from the surgeon, the endoscope shaft gets moved away also. It has to point toward a different position. And we will try to use the flexible endoscope to bend the point of view back to maintain the view. Okay, so that's the idea. And there are people who do relatively similar works, but they always have something different. This is a result from, I believe, from Singapore, University of Singapore. They have quite a lot of degree of freedom to control the flexible. They didn't use it for endoscope, but they were using it for a flexible manipulator. You can see that they can achieve a very regular trajectory. And there's this is a very famous paper by Oak. He came up with a model for the bending tip. And so what we turned, but we basically working on a long, flexible robot. So what we did is we kind of took the part of the bending tip and used that to model our flexible endoscope. And then effectively we have 2 more degrees of freedom for our robot. So when the robot arm moves and the shaft moves, we'll be able to bend the flexible endoscope back toward the image. Okay, now I'm going to show you the first version of the system. What we have is we have the robot, and then we have the RCM program and the task control program in a computer, and then use that to send it to a driver for the control. And then also we have a separate controller for the endoscope tip, and using that to control the endoscope. So this is how it works. And if you are familiar with the endoscope, you will know that it is actually not a very friendly device to play with. When we took apart, we actually had I believe somewhere around 600,000 Taiwanese dollar surgeon grade endoscope. And then we took it apart because we wanted to hook it up to a motor to control it. And we actually broke it, so it was gone. But we actually found another one, which is this one. It's less expensive. I believe this one is probably somewhere around 200,000 Taiwanese dollars. It's an industrial grade endoscope, so we try to use that. But this one has one less degree of freedom. If you recall the endoscope, it bends both in 2 degree of freedoms. So we can not only bend in one in yaw and pitch, but this one doesn't. It only has 1 degree of freedom bend. But we have the robot has a 6 degree of freedom on the end of the end effector that kind of rotates. So we use that to compensate for the missing degree of freedom. Okay, now the kinematics is when you look at the slide, you may think it's a very kind of complicated mechanism. But actually, if we look at it closely, what it does is we were modeling the flexible endoscope, the curve of the flexible endoscope as part of a circle. So this is actually just an arc. And when we use 2 cables to control the bending of the flexible endoscope. These 2 cables usually are located at the 2 direct angle of the endoscope. So how do you bend it? You bend it by shortening one of the cable and compare with the center line of the endoscope. There will be a difference. This difference shows you the difference between the arcs. So you can just reverse calculate divided by the diameter. You'll be able to come up with the bending angle. And once you have the bending angle, you can control the pointing. So this is how it works. So I guess you can see how simulation. But we can do that in simulation, and we can also do that by the actually endoscope. Now, if you combine all these tasks, you will see we have 3 levels of tasks. We have an RCM control by actually no space projection, and because of the no space projection, we also have task control, and then we also need to compute the endoscope control. So it becomes kind of a bit tedious as far as the computer is concerned. So we came up with a different type of RCM control. Instead of just using no space, because we needed no space for too many things. Instead of no space projection, we use a different representation of the endoscope. In order, what we get is using that to instead of having to use a no space projection, we use this expression as a kind of an additional joint, and using that we can avoid the no space part for remote center of motion, and then use that use the remote center of motion control. Use the task control only for to react to the surgeon. Okay, so that's what we did, and what we did is using the trocar frame. If you the trocar shaft, you use a additional parameter to describe the distance, location of the trocar shaft through the patient's body, and use that we can get an additional joint-free additional parameter, and using that we don't have to worry about the task control for remote center of motion. And I guess we're not going to go through all the other details, because what we did is we have two levels of control. One control for the robot attitude, and the other control for the distance between the shaft position and the desired remote center of control. So that's what we get. And the control actually is pretty straightforward, because what we did is only an additional parameter, so it's not going to be too complicated for calculation. Now, the funny thing is, the control itself is only, if you look at the previous slide, the control is in the joint space, joint space operation. So we always feedback the joint space error, but the actual position is in the physical space. So you needed to be able to translate the physical space error or task space error into the joint space. And that may sound easy, but when we want to use it for feedback control, it becomes not as straightforward. So what we did is, this is the error we measured from the task space. And we try to use a Jacobian projection to project these errors into the joint space, but using that as kind of decontrol. And that is actually not very, not very intuitive, because we are projecting task space error into joint space, and they use that to drive the joint space motion. But somehow it worked, and we do have the proof for it, but the proof is actually quite sloppy, so I'm not going to show it to you. But basically, we can show that the error does not diverge. But I can only guarantee the error does not diverge, but I have the problem showing that the error converges to zero. So we have a bounded error, but not exponentially converging error. But anyway, somehow it worked. So it becomes something like this. Now, there are actually a lot of details concerning the control of the bending angle. Suppose we think about this as our target viewpoint. So this is where I want you to see, and consider this is the rigid shaft of the endoscope. And when we move, suppose somehow the lower arm moves, and the shaft has to tilt by or drive by an angle of theta. What you see is because of the motion of the shaft, of course your endoscope gets moved away. So we need to try to bend it back, and this is the angle we need to compensate for. So we need to bend it back for an angle theta prime. And just using the geometry, you can easily calculate the theta point from theta. So that part is straightforward. But because the endoscope itself has a dimension, it's not like an infinitesimal endoscope, right? So you have, you do need to consider this part of the size of the endoscope. So in addition to the length of the shaft, you still have an additional length created by, just occupied by the facial endoscope. So what we did is we come up with this equivalent model, and that equivalent model including one linear actuator and a rotary actuator. Using that to, actually we have two rotary actuators because the endoscope also rotates sideways. Using two rotary actuators and one linear actuator to model this. And with that we can, the geometry is a little bit more involved, but it's still doable. Basically we come up with a new expression for the angle to be compensated. And once you have the angle to be compensated, things becomes more straightforward because we can always try to bend the endoscope toward the target viewpoint by bending it at the correct angle. Of course, we do have problems because of the sloppy setup we have, because basically many of the stuff, the robot itself is bihybrid, so it's pretty accurate. But everything behind that, the endoscope was like we tear it apart and try to put it back together. It doesn't really work that well. So there's always error, and we try to use an iterative process to kind of minimize the error. Okay, and of course there are different ways we can compensate for the angles, but this only works for my original design, because originally I have 2 degrees of freedom bending, and now I have 1 degree of freedom bending. So, well, by using, instead of using the 2 degrees of freedom bending to bend it back, we use 1 degree of bend and then rotate to get the image. Okay, so these are the homogeneous transformation matrices that if you are interested, you can see. So now we have an additional part of the algorithm for the bending angle. And everything combined together, you will see some of them will work. So you can see that in simulation it's pretty, because everything is precise, so it's kind of easy. You can see that the robot may move around, and I will always maintain the remote center of control, and also in addition maintain the target viewpoint. Now, I kind of like this movie, so I'm going to make it play a little bit more. Okay, and if you look at the control arrows, remember before I described the control law by projecting task space arrow into joint space, and somehow I didn't project it, I only drove it, and somehow it worked. If you are an expert in robotics, you'll know that usually what we need to do is you need to project the task space arrow into no space, and then use that arrow to drive the joint forces. And somehow that's what works. So, forgot what I was trying to say. Okay, and this is one way we try to achieve the surgeon cooperation. The NIMBY small mass model is actually created by Professor So. He was doing impedance control, and with the small mass model, he was trying to get the robot to act like a small mass so he can easily put it away. And basically, it's just impedance control, so we use that. And this is a software developing environment, and I guess if you are a robotic expert, this is pretty standard. I suppose we have, okay. By this movie, I was trying to show you, when you try to hold the remote center of motion, the remote center of motion can be observed, but the position of the control car actually moves up and down. So you needed an extra parameter to describe it. Now, here is the endoscope tip. And you will see that when we move the robot, the tip will bend, always try to bend toward the target. And I know you will be skeptical because you can't really see how the tip bends. And this is an image taken by the endoscope. And you can see that when the robot moves, somehow you always bend it back and try to maintain the target. Of course, like I told you, the robot is a pretty precise and good Taiwanese-made robot, but the endoscope was taken apart, so it doesn't really react as well. But anyway, this is what we achieved. You can see that it's serving its purpose. Okay. Now I'm going to show you another part of our research. I believe this is also interesting. Endoscope is only, of course, it's a crucial part of the operation, but it's not going to replace the surgeon. So when this is after like 6 years of cooperating with the surgeon, he started to say that it would be nice if the robot can kind of replace him. And it's very hard to just replace him, right? So what he asked us is that when he started suturing, suturing is an easier word for you guys, is sewing the wound. Okay, so that's called suture. And when he started the suturing process, it's usually a very tedious process because kind of you stick the needle in and pull it out, and then tie a knot and then stick it in and pull it out. So it's tedious. So what he asked us to do is, once he started the process, can we use a robot to finish the work? So at first I thought it was a challenging and a pretty interesting task for me to do. So I said, sure, we try it. But I later realized that it was not really something that's easily achieved, and we kind of only have similar results. But the results, I think, is interesting, so you guys might want to see it. Okay, so there are, we started out with a tool used by Da Vinci. The Da Vinci tool has a very neat tip. This is the tip. We use, the Da Vinci call it the pusher. What it is, there is a 2 degrees of freedom wrist, and then there's a grabber in front. So you can grab the needle and use the wrist to kind of sew, to perform the sewing motion. So and we use a different robot, and the reason is quite easy because I don't have the money to buy the robot I want. And then the other robot is still being used for endoscope research. So we've got a different robot. And if you guys, some of you guys might recognize, the other robot is by Tyree. This robot is by, I don't know if it's English name, Dani. It's actually a pretty neat robot. It's a human cooperating robot. It has the built-in ability to react to human touch. So it can only stop. It doesn't really, like I showed you first, it doesn't avoid, but it can stop. And this is the end of the detailed blow-up figure of the Da Vinci tool. It's got 4 driving wheels, 2 for one set. These driving wheels drive the cable that drives the wrist, so the wrist can move around. Okay. And we came up with basically a driving device to hook it up to the Da Vinci tool to drive the robot. So here we have a standard robot, and we fix the pusher on the end of the robot, and then we also use Arduino. I didn't like the Arduino, but the student are familiar with it. So and this is a very simple task. So I use Arduino to control the angle of the servo motor to drive the pusher. Okay, and I guess you don't need to worry about too much about the DH table and the dynamic control part is actually easy because once we already established dynamic control of the endoscope holder, this is basically the same. But for the endoscope holder, we have to worry about the surgeon being around, so you need to kind of get out of his way. And in this case, surgeon's gone, so there's no need to worry about surgeon anymore. And the control becomes more straightforward. You only have to make sure that it follows the path. So the control loop is a little bit less complicated than the previous tour. And also we need to observe the entrance wall. So we still have to maintain the remote center of motion. And still, instead of using the no space projection, we still use basically the remote center of motion point control. Okay, now the control is basically the same, so I'm going to go through the detail, and we try to compensate for. Sorry for I'm pretty sure I corrected the format, but somehow didn't like it. Wow, anyway, this is a detail of the wrist. You can see that we have this grabber, and then 1 degree of freedom grabber moving around up and down, and then sideways. So you have 2 degrees of freedom plus the grasp. If you don't count the grasp, there are 2 additional degrees of freedom for you to play with. So with the Da Vinci needle pusher, we have actually 8 degrees of freedom in remote control. So it's a fairly sophisticated system. And you can see these are just the homogeneous transformation you might want to go through if you like. And now the sorting path. This is actually suggested by some surgeons. When you use the needle itself is part of the arc. So you try to use a semicircle path for the needle that was suggested to be a very good toe path. So this is what we get, and we try to achieve the path. And now I wanted to remind you that we are using 2 additional degrees of freedom to drive the needle. So we have 8 degrees of freedom total, but we have already a constraint of remote center of control. So we have 7 degrees of freedom, and that is what we end up with. And what we did is we changed the tool path into a parameterized path, and for the robot to follow. And I guess these are details you don't really need to know. And I guess what we implemented now, we have robot posture control, and in addition we have wrist control because we have these 2 additional degrees of freedom. But we only use 1 motion planning, and actually once you computed the trajectory, you can break it up into different joint positions and then send it to the robot to reflect the position. And this part is quite is less complicated than before because we don't have to worry about the surgeon avoidance anymore. And I think it should work. And you need to see that we are observing the remote center of motion and we're driving the needle. Okay. And this is the control error observed, calculated from the robot wrist. So it's not the in situ error, but it's a calculated error. And I wanted to show you. I'm sure it will work. Yeah, it's doing it, but it's very slowly. And this is a imitated meat. It's got almost the same toughness as human skin, so it's very hard to penetrate. We can see that we're doing it. Now, this is actually the second to the last slide. If you think about it, you can see that the needle gets pushed through the skin and kind of complete a curve. But if you observe it closely, you'll notice that the shaft actually gets kind of pushed away because the skin is because it's very tough skin. So what happens is when you drive the needle through, you don't really know where it comes out because of the deformation. So I'm going to show you one last slide that you might feel very interesting. Yeah, it's driving it. And the previous slide only shows you half of the test. You drove the needle through, but what we really need to do is you need to pull the needle out and then tie the knot. And you can see that the skin is actually very tough, so it's very hard to penetrate. But you can see that the driver gets pushed away and the needle comes out, but you don't really know where it is. And I challenge my students, he will not be able to graduate unless he will be. So that's why he did it. So he graduated. Okay, so that's what I have to share with you today. And I believe all the math you need is there. And if you are a body expert, many of the material I show you are kind of standard. I kind of put a different aspect of the previous robotic research results together to form the entire system. And I will be happy to entertain any question you have.
谢谢严老师非常精彩的演讲。那么在下一招跟主持人先，同学有提问的，来请举手。
要讲英国语啊？讲英文透。
OK， 来，我们有同学。
谢谢老师。我想请问一个很基本的问题，就是说，就控制的观点来看，那对这个就缝线的这个，它最大的挑战会是什么地方？就是说，
说的好问题。因为其实叫这个 robot arm 去走这个路径很简单啊，我根本连控制都没有，只是把那个路径打进那个现在的 robot 的 controller 都可以容许你打路径进去，打它就走出来。我还嫌它太慢，因为那个照理说这个 robot 没那么笨。Are you guys okay if I answer everything, or should I repeat it in English for you? The question is, what is the? I forgot the question. Yeah, the challenging part of the surgery. First of all, you only have a two-dimensional image from the endoscope. There's no three-dimensional information. So how do you know where to stick your needle? You can see that it's there, but you only have 2D information, so you need to kind of guess how far it has to go to reach the position where you need to sew. That's one thing. And the real difficult part is, and once you stick it in the needle, you notice that the shaft is pretty long, and you're holding it at the end. So once you stick the needle in, you started to feel the resistance of the skin, and the shaft gets actually pushed back a little bit. And once it gets in, the shaft has to counter all the resistance of the skin and the tissue. And so it further bends the shaft and actually moves the needle away from where you originally planned. So after your needle comes out, you only have 2D information of the tip of the needle, but you don't really know where it is. I actually don't know how my students got that. I did kind of how do you say that? Interrogated him, and the answer he gave me is he did a lot of trials, And what we're doing right now is you actually have certain part of the 3D information. You have the skin. You know the dimension of the skin. You know the tip, position of the tip because it's at the end of the robot. So if you have these information, you know where the tip is, and you can use that as a reference, and then use the dimension of the name 仿体啊，中文 the imitating meat. Use the dimension to kind of provide you information of the environment. And of course, you have the tip of the needle, right? And somehow you can guess where it is and try to grab it. We will try to do it right now. And I guess one interesting thing is we came across a paper that was discussing the resistance of the needle. So one other approach for this is probably to calculate the resistance and use that resistance to calculate the bending of the shaft, and then use that to derive the position of the tip. That's what we're working on right now. I'm not sure how it's going to come up, but it's a challenging and interesting problem. And I really need to add one thing. Desoldering are becoming less popular. If you are familiar with the operation, you notice that the most recent use was using stapler to just staple the wounds together. And they are very neat and come up with the wound. They stick the wound together very neat. And many of the staples are dissolvable by body. And so I'm not sure how long will the suturing last. But I also noticed the surgeons are still using that. They're still suturing patients. I'm not sure how they judge whether to use a staple or use a suture.
李教授你好，又见面了，很高兴看到你，真的非常精彩的一个演讲。那有一个小问题请教你，那个像这个机器手绘6轴或是7轴，它如果10部摆在一起，不同的那个它的那个 configuration 或是它的那个机构的材质，它总有一种会最适合做刚才同样的动作。那您这个计划里面，或研究里面有没有针对 optimization， 就是它的机构的部分？
非常好，谢谢你。确实，我们这一次很不适合。你看到我做这个小动作，后面呢这样乱搞半天，确实非常不适合。那我们现在在试一支7轴的，不过我老实跟大家报告，这一支我是花好像40几万买的。40几万是因为我去孤立我的学生，他是那个公司的老板。你要真实买的60几万，那刚才那一支上映的那一支可能也是60几万，那我是要他们半买半售，也就是说，以我们教授的薪水跟我们的 budget 的范围，老实讲买不起这些玩具啊，所以确实没有能力去做那个。但是我们后来我又不有另外一个学生买了一个7轴，那支我好像花了50几万这样。那大家知道7轴你要买到100多万以上。我们现在在试那个7轴会比较好一点。不过您说的对哦，我其实是可以做这个分析，但是我确实没有那个钱可以去弄那么多罗马来玩了，所以当时确实还没有想，这确实是一个好主意。好问题，看来做好问题，因为这个 pass 你买吃掉了，所以这里2个就可以吃掉。吃掉了，我机器手有，对不起，因为这支比较特别，对不起，我刚没仔细跟大家报告，这支跟刚前面那支不一样，前面那支我用的是达文西那个 wrist， 所以它有这个跟这个，所以8个苹果吃掉。那我要做这个 dimension， 做这个绝对可以，可是这一支我其实前面大家没有注意那个上面上面只是夹着一个普通医师用的布而已。所以我少了2个 degree， 那少了2个 degree， 我还要产生，我已经在那个 remote center motion 被你逮到，那边就已经吃掉3个 degree， 所以我只剩下3个6支援，也就是说我其实没办法反映这个 pass 被你逮到。我现在做的其实是想办法大家可以实现里面去 map 出一个最接近的 pass， 其实斜，本来是我用那个达文西我可以直接这样切进去，那现在是斜的，被你逮到。
因为那个 staple 一般来讲是好像是暂时的 temporary， 把那个问题把它 staple。
谢谢你，这让我很安慰，我白做了半天。
没有那个用那个缝线当然是会比较 permanent， 可以让它伤口一个切开的伤口是可以比较缝起来，因为我们
看你技术啊，你缝的乱七八糟。
因为那个人手的 degree 比那个机器的多多。
对，
很不容易去用那个线去那个手。
你说的没有错，我们其实有做一件事情哦，我们用那个，你知道那个有那个3个球的东西，我们让医师抓着进去缝，然后想办法去还原医师的动作，用机械就还原不出来。你说的没有错。
同学有疑问吗？想问一下严老师，现在都是一只手在做缝线动作，如果2只手有没有办法提高成功率？
绝对有，那没有对这个缝来说没有用啊。可是当我这样戳进去以后，这边放手，如果有另外一只直接把它拉出来，就会快很多。而且有没有大家如果刚看那个电影哦，你戳进去以后戳好放掉，那肉又弹走了。换句话说，我本来是因为我抓着我知道它的位置，它弹走我就不知道它的位置。所以我如果第2次我把它说过去我不要放，第2次就把它拔出来，第2又快，我要找那个位置容易。我本来是要这样做的，是没钱买第2次啊。大家不要觉得我很有钱哦，我们其实科技部其实不是那么大方啊。
同学有兴趣的要提问的吗？
老师你好，就是如果说从那个洞到肉的中间有一个障碍物的话，机器有办法自己闪开来吗？
哪一个？你说这个啊？
对，就比如说从那个箱子的洞，它有办法从
这边哦。如果我知道那边有障碍的话，是可以闪得开。可是你要有足够多的 degree of freedom。你目前的状况，我其实终于用完了，我再闪它我就不能缝了。
那有办法就是，如果说知道那边有障碍物，就是你在钻洞前你就先选好一个最好的洞嘛。
会，你这其实是另外一个好问题。医师在病人进来之前，他会把它 CT scan， 然后他会去算说我要在哪里切个洞，刀子会正好进到我要的地方。那个确实事先就会做，没有错。
Any further questions from the audience?
不，如果你们大家时间太多，我还有很多可以讲。真的要我再讲？没有，我还有别的研究，其实蛮好玩的。我们可以讲几点？
到5点半就可以。
5点半是好。
没有，可以提前结束。
原来是这样，因为我本来以为我们想到4点半，到
5点就好。
5点半，因为大家真生气了。Okay, I'm going to show you another research result. I believe it will be very interesting also. And because I didn't know it in advance I'm going to talk about it, so the title will look a little bit awkward. Sorry about the title, but I mean the background. But this is another project I work with the hospital, and instead of the surgeon, we're working with ophthalmologist in Korea. Okay, and what we're trying to do is trying to diagnose keratoconus. Keratoconus is a disease. I will show you the picture. Okay, so. Basically, what we started with is when we started cooperating with the ophthalmologist, we were trying to come up with a better way to measure the mechanical property of your cornea. The doctor I work with is the chief of the ophthalmologist department in National Taiwan University, and he is an expert in cornea related diseases. And one of the important problems we have right now is if you has anybody went to the ophthalmologist before? Anybody has experience? 就有没有去看过眼科？都没有，你大家那么健康。Anyway, when you go there, they will basically do two things before the ophthalmologist will look at you. They will get you to sit in front of the machine that measures the nearsighted or farsighted optical property of the eye, and then they will get you to sit in front of another machine that shoots a small jet into your eye, and you don't know what it is for. Did anybody has been shot before? 没有，有吗？喷一下的。Okay, what it does is it shoots a small jet into your eye and measure the intraocular pressure. Intraocular pressure is the pressure behind your, actually it's the pressure behind in your eyeball, the pressure of the liquid behind your cornea. And why do they need that? Intraocular pressure is a very important indicator of the healthy condition of your eye. And it can cause, too much of the intraocular pressure can cause your retina to deplete from the back of the eye, and that actually actually causes blindness. So it's an important measure. But the problem with the measurement is that if you are familiar with the machine, once the jet shoots into your eye, they take pictures, and I will show you those pictures. They take actually continuous picture, and then they calculate the response. And they come up with a response. They calculate many parameters. The parameters include the time it takes for the maximum deformation, and also the area of the deformation, and then also the time when it started to deform and the time when it comes back, and then also because of the hysteresis of the eye, there will be a delay. A difference between when you started and after then it comes back. So there are a lot of parameters, and because of the Shenfla image, they kind of take a sheet of your eye, kind of cutaway view of your cornea, so they can also measure the thickness of your cornea. So there are a lot of parameters, and with that parameter, they come up with pressure. By the dynamic response, they come up with pressure. But the problem is, for many of you are mechanical engineers, you know, with the same deformation, but different material, the pressure actually can be very different. And the different material, by different material, I mean the stiffness of the cornea, and that translates into the Young's modulus of your cornea. So we wanted to see by still looking at the same images taken by the machine is called Covis. But with the same information taken from there, will we be able to extract not only the more accurate intraocular pressure, can we also extract the Young's modulus of your cornea? So with the correct Young's modulus, we can correct the ocular pressure, intraocular pressure, and give a better diagnosis. So that's what we're trying to do. And of course, later we wanted to see if we can further use that to help the ophthalmologists to diagnose some of the disease in this early stage. So this is, sorry, I use a lot of terms that I myself are not even, I'm not even familiar with. Okay, this is your eye, and there are an anterior chamber where it's also filled with fluid. The fluid comes from the vitreous body, so it's basically the same as the fluid in your eye. And the cornea is on this part of your eye, and of course there are pupil and other stuff there. So when we measure intraocular pressure, we are measuring the pressure in the blue part of your eyeball. Now, of course, there are tendencies in there. I'm going to go through with that because I don't have enough time for all that. But probably many of you don't know this term again. This is called glaucoma. Is translated to measuring 青光眼. So it's a very if you look at the trend, it's a very popular disease, and it can cause blindness also. So we started out by trying to get to give the ophthalmologist a better measurement of the intraocular pressure, because that is directly linked to glaucoma, and we try to see if the glaucoma we will be able to predict or give the doctor a better description of the intraocular pressure for his diagnosis. And then keratoconus. Now I'm showing keratoconus. Mainly for keratoconus is 圆锥角. So what you see is the cornea forms a cone kind of shape, and you probably feel like this is a real disease. No, it's a very popular disease. Even my own daughter suffers a little bit of keratoconus. And of course, if you know in advance there's a problem, there are ways you can try to, probably not cure it, but you can try to maintain it at a controllable stage. So early detection of keratoconus is a very important task for the ophthalmologist. And if you look at it, probably a very intuitive way for diagnosis is by looking at the shape of the cornea. But once you can observe this kind of keratoconus, the patient is basically helpless. So we wanted to be able to diagnose the patient before you can see it. So this is part of our research. Okay, and the main diagnosis tool at this moment is a tomography. The system can actually give you this kind of the topography of the cornea. So if you look at the shape of the topography, usually you pretty much will be able to tell whether the patient has some problem. But still, it is not a very obvious way. It is not a very sensitive way of diagnosis, because you really need to have the cornea has to already be formed before the topology will show. So this is one thing that the ophthalmologists did really are not happy with. Okay, now, like I said, the present day measurement of the intraocular pressure is by shooting a jet. But before, what the doctor really do is what we call Goldman tonometer is they actually make you lie down on the bed and use a small hammer to drop it to your eye. It actually touches your eye. And yeah, because after all these years I've worked with ophthalmologists, I noticed your eyeball is not as delicate as you thought. You can touch it, you can cut it, and it will still heal. So it's actually pretty okay that you can touch it. Now, this is a new machine that there are kind of quite a few variations of the intraocular pressure machine. There are contact tonometers, and the most recent or more advanced machine use two different things. One is they take the picture of your cornea. The other one shines a laser on your cornea and pick up the reflection of the laser. And when the jet touches your eyeball, the cornea starts to form, and the laser gets picked up, and then the eyeball started to form, right? So the laser, the position of the laser started to also bend toward the extreme point, and after the air drops, you see a rise. The cornea bounces back, and the laser will bounce back. So you can pick up this kind of signal, and that gives you a lot of information. For example, when it started to bend, and how deep does it bend? Also, the difference between the undeformed cornea position and the deformed cornea position. So you have a lot of indexes you can use. Now, the non-contact, like I already described, the non-contact tonometer does not like when you drop the hammer on your eye, because it achieves a dynamic balance, so the pressure is correct. But in this case, everything is moving, so you kind of try to estimate the differences, and many times your measurements are very dependent on the stiffness and the mechanical property of the cornea. So what we're trying to do is this is just saying that, okay, now the cornea itself has kind of a very complicated structure. It's got layers of different materials, and usually I believe the stroma occupies the bulk of the cornea, but there are also this layer, bonus layer, which is the strongest layer. So this one single layer determines the stiffness of the cornea. Well, this is just background material, so let's not worry about that. And there are a lot of approaches to try to model the cornea. So I'm not going to go through that, because I just want to show you the result, because we are getting. But this is interesting, because we are actually able to calculate and come up with this analytical result between the deformation and the applied pressure. So it's a pretty neat result. We can use that to calculate the Young's modulus. And the funny thing is, you can't really measure the Young's modulus of the human cornea, because you cannot get a patient and cut a piece of the cornea and then measure the Young's modulus, right? So we always try to estimate. And then there's one way you can actually measure it is by taking it out of the cadaver. Cadaver is but basically it's already dead, so it's probably not very similar to the living cornea. They are different. But we did use our measurement using that formula I showed you. We were able to calculate the Young's modulus, and we kind of try to establish a correlation between all the established publications. But if you look at the publication, there is really no definite answer of the regular cornea Young's modulus. The range is all over the place. But anyway, this is what I wanted to show you, the dynamic model. Using this very interesting machine called this ST, it takes the picture of, it takes a slice of your eye and shows the deformation. And we believe this information, this dynamic information contains many information that are not being explored. So we try to use that. And then what we did is, well, let's not worry about this. What we did is, first of all, we need to come up with a dynamic model. So what we did is look at the liquid filled sphere, and then look at the dynamic response of the sphere, and try to use that to model the part of the cornea. And you can see that we were actually able to establish a dynamic equation, and use the dynamic equation. What we can do is we can look at we can do the separation variable, and then calculate the motion. And once you have the motion, we can try to match our measure response with the motion. And because of all these parameters that's embedded in the equation, we might be able to extract all the desired parameters. Now, there are different modes. Let's not worry about that. And this is, if you want to see that our response, you can measure the motion. Now, we needed to these are the motions. Now, this is actually the real measurement, right? And we needed to check the response. So what we did is we used some of the image processing technique to extract the curve. And we get that curve, and we can compare the center point, the formation, the displacement of the center point to compare with our measurement. You can see that the comparison is, sorry. And then we use, recall I kind of composed all the motion, right? So I can recombine these motion to try to fit it with the response. And once you come up with a very decent fitting, you'll be able to use that fitting and then extract all the parameters out of it. So this is what we did, and this is our estimate damping Young's modulus. And you can see that the Young's modulus lies in a very wide range. Started out from 0.0 something all the way to 0.7. So it's very big range. But nobody can say that this is wrong. Nobody complain, because all the measurement results are kind of similar. Now, we also wanted to see if we can use the dynamic response to see if the shape is wrong. So we also did that. And this is a keratoconus eyeball cornea. This is a healthy cornea. You can see that the motion is slightly different. The keratoconus has a lot more movement. I guess because the cornea is weaker. And you can also do the similar decomposition and analysis. And I didn't put the rest of the result here, but we can decompose all the motions and coefficient of motion and use that. We are now trying to decide whether the eye and cornea is healthy, and the cornea has problem. And so these are some of the what we did is, instead of that motion I showed you, we do the Legendre polynomial and use the Legendre extension to describe the shape of the cornea. So with this, we kind of decompose it into different modes and use that mode, and we can describe the response, and we try to compare all the responses with our first phase of research. We collected 140 images on the patient and compare them, and also we decompose the modes. And you can see that different patient gets very different responses. but there are trends of the modes. So what we did is we compare the response at a different stage, and then use that. We also use that to kind of provide the doctor with hopefully a better judgment. We haven't been able to come up with a very conclusive result because you can see that the responses are very noisy. So what we did next is we try to come up with an artificial device to help us compare with our results. This is a proceeding eye, and you can see that proceeding is a 猪，用猪眼睛来做事。And you can see that we come up with a very similar result as human eye. And we will be able to cut holes on the eye and probably actually impose some images and try to see if we can do better. But I guess we're not totally conclusive yet. But you can see that we are doing the kind of research that are very interesting. What we're doing now is we try to collect more of these responses and try to see if we'll be able to separate different diagnoses out of these responses. And sorry because I didn't have enough time to get a better proliferation. So, but if you like, I will be very happy to answer your questions.
袁老师 is a very interesting talk that across the discipline.
谢谢袁老师，这个我自己有很多经验了。我在那个新竹光复路有一个谢生祥视眼科，他每次去都会喷个气，我有以前很多次经验。可是我每次去的时候，我都很好奇说，像我们他怎么知道要喷气的那个 press， 到底要有多大的 press？
那个 pressure 是固定的
，pressure 固定，
那个时间那个 pulse 的强度跟时间都固定，就每个人都一样，
每个人都一样。
没有，你其实问了一个好问题，我们会躲嘛？
对，他每次都叫我就卡在那边，然后
你手握要贴很紧，
对，贴很紧。
那大部分人，我相信你们大家都一样啊，他一喷一定躲，那结果一躲的结果就量错。那量错如果太明显的错，它就像虫那样，很多时候你不知道因为看你躲的不是很明显啊，那就会错。
那对于这个年轻的跟年纪大的，他们因为眼球也会老化，所以这个会不会对你
会？其实有些人做那个研究，老人家的样子module好像是比较小一点，可是因为那个 range 实在太大了，他们从死人的量的从尸体量的跟从那个病人量的，早上量晚上好像都不一样。所以我们可以那个范围，刚刚大家看到我不是说0.0几吗？有0.几，而且几乎快到1，对不对？那种都有跑，可以说是对的。
所以他那个就是他都只是跟我说测，他是有压正常的，那包括连那个青光眼也可以测。
没有，他是这样，青光眼是被眼压引起，对，所以。其实很糟啊，因为等到你青光眼的时候，已经那个角膜被压迫，已经出事了。
谢谢你，解了我很久的，因为为什么要喷一下这个，我就一直搞不懂。
对，那个对眼科医师来说很重要，你眼睛健康不健康 ？Sorry 啊，we were talking about this jet machine. When you go to a ophthalmologist, the ophthalmologist will always ask you to go to this machine and take a measure. It actually shoots a small jet into your eye, and the purpose is to measure your blood pressure. Sorry.
Any further questions? If not, let's take from Yen again. 话里面的这个分享，谢谢。
重蹲，我觉得站位。 进化已经不用再站位。
但是我要抢那个凹槽，我要旁边那个凹槽。
那就这样吧。他又不说上厕所是哪一个？每次上厕所都不同的，我都同一个都有。太难，这个我靠他。好，我的好，谢谢，好，拜拜。也有问我们希不希望范围大一点，不要那么大，也是可以。没有大家都不要，然后说不要，但是唱给我好看的时候，对，不准。一毛，你会把你的一毛对吧？有什么好看的？拿起来，哦，也修不好。
神经病有时候我们考试会看，所以你不要考试的时候胡言乱语。